Today, we're jumping into the wild world of high-tech manufacturing, where the future is literally being built one atom at a time. And we're going to see how scientists are borrowing a 3.5 billion-year-old idea from nature to solve one of the toughest challenges in modern engineering.
So let me ask you this. Imagine you're trying to perfect a recipe, but all the ingredients, the temperature, the mixing speed, the timing, they all interact in ways you just can't predict. You change one tiny thing, and the whole thing could be a disaster. Now, what if those ingredients were atoms, and your recipe was for, say, a critical component in a satellite? That's the challenge we're talking about today.
So here's our game plan. We'll start with the problem itself, a super complex process called sputtering. Then we'll look at the brilliant solution, which is inspired by nature. We'll see how it's actually applied, check out the incredible results it gets, and then look at what this all means for the future.
All right, first up, the sputtering puzzle. This is where we'll really dig into just how mind-bogglingly complex it is to create these perfect, ultra-thin films that our entire digital world runs on. So what even is sputtering? The easiest way to think about it is like atomic spray painting. Seriously, inside a vacuum chamber, you blast a target material with ions, which knocks individual atoms loose. Those atoms then fly across and deposit themselves onto a surface, like a silicon wafer, creating a perfectly even, incredibly thin layer. This is how we build everything from the chips in your phone to cutting-edge solar panels.
Now, here's what makes it so tough. To get that perfect film, you have to get all of these control knobs, so to speak, just right. But here's the kicker. None of them work in isolation. You change the power, and that changes how the pressure affects things. You tweak the gas mixture, and that completely alters what the power is doing. It's this giant multi-dimensional puzzle with no obvious answer. When a problem is that tangled, where do you even begin to look for a solution? Well, you turn to the greatest problem solver we know, nature itself. This brings us to a solution that's been in R&D for about, 3.5 billion years. And that solution is a type of AI called a genetic algorithm. Just like the name sounds, it's an algorithm that literally mimics the process of natural evolution. So instead of trying every single possible combination of settings, which, by the way, would take centuries, it intelligently evolves its way toward the best possible answer. So, how does it actually work? Well, you can think of it like a three-step dance that just repeats over and over. First is selection. The AI tries out a bunch of different sputtering recipes and keeps only the ones that work the best. Next is crossover. It takes the best parts from those winning recipes and mashes them together to create a new generation of even better ones. And finally, mutation. Every once in a while, it throws in a totally random change, just to see what happens. You never know, a random tweak might lead to a huge breakthrough. It just runs this cycle again and again, getting better each time.
Okay, so that's a really cool concept, but how do we apply it to our manufacturing problem? This is where we start treating those process parameters like they're a genetic code that the AI can read and, more importantly, optimize.
Each one of those control knobs we talked about, power, pressure, gas flow, it becomes a gene in our digital DNA. Power, for instance, has a huge effect on how fast the film gets deposited and how dense it is. Pressure is a big factor in the film's compactness. And the gas flow? That determines the exact chemical makeup. The AI's job is to find the perfect genetic sequence that creates the ultimate material.
Just look at one single gene, power. You might think, okay, let's just crank up the power to get the job done faster, and for a bit, that works. But if you push it too far, you start introducing tiny defects, and the whole film becomes weak and unreliable. There's a perfect sweet spot. And a genetic algorithm is absolutely brilliant at finding that sweet spot, not just for power, but for everything else, all at the same time.
Let's take another one, pressure. It's pretty straightforward. The higher the pressure inside that chamber, the more the little atoms get bounced around and scattered on their way to the surface. And what does that mean? It means you end up with a film that's less dense, kind of porous, and just not as high quality. The AI has to learn this and balance it against all the other factors. And then there's the gas recipe. Most of it is an inert gas, something like argon, that doesn't really do much. But there's always a tiny fraction, maybe just 5%, of a reactive gas like oxygen. That tiny slice of the pie is absolutely critical. It defines the final chemistry of the material. If you get that ratio wrong by even a tiny bit, you might as well have made a completely different thing. So, we've got this incredibly complex problem and a super clever AI solution inspired by billions of years of evolution. But does it actually work in the real world? Oh yeah.
This brings us to the most exciting part, the payoff.
Now, what's really fascinating is that the best results don't just come from the genetic algorithm alone. In a landmark study, researchers used a hybrid approach, basically an AI dream team. They started with something called Taguchi methods to get some really smart starting points. Then they used an artificial neural network, or ANN, to predict what would happen without having to run tons of expensive tests. Then they let the genetic algorithm loose to explore all those possibilities and hunt for the absolute best solution. It's a team of specialists, and each one is crucial.
And the result? By using this team approach on titanium-thin films, they achieved a 98.8% reduction in the deviation of electrical resistance. Just let that number sink in. That isn't a 10 or 20% improvement. That is a near-perfect elimination of any inconsistency. This is the kind of breakthrough that lets us build the smaller, faster, and more powerful electronics that we all rely on. It is a massive, massive leap forward.
A result like that doesn't just solve a problem, it opens the door to a completely new future. And that leads us to our final thought, where this is all headed. We're moving beyond just optimizing a process once, and toward a future where the process adapts in real time.
You know, you can really see the evolution of the process itself right here. We started with engineers literally turning knobs by hand using trial and error. Then we got smarter with statistical designs. Then came the predictive models. But the final step, where we are heading right now, is a fully adaptive AI that uses these genetic algorithms to correct and improve itself on the fly. The ultimate goal here is something called a digital twin. Imagine a perfect virtual copy of the sputtering machine running on a computer, in sync with the real one. The AI would get live data from sensors on the real machine, run millions of evolutionary simulations on the digital twin to find the perfect adjustment, and then apply that fix to the real machine, instantly. It's a system that guarantees a perfect result every single time.
And that really brings us to the final big picture question. We've just seen how an AI that thinks like evolution can completely master a process at the atomic scale. So if AI can learn to evolve better materials all by itself, what other huge, impossibly complex challenges in medicine, in energy, in space exploration is it going to solve next?